Page 376, section 3.5. It's about rational functions and their graphs. So just like everything else in this chapter, we've been really focusing on how to draw the graphs of these different things. Y'all are doing a great job with that, by the way. I was really pleased with those quiz grades. For the most part, they were really good. The very last grade. So, objective 1 talks about finding the domain of a rational function. First of all, I guess we need to talk about what is a rational function. Anybody remember what a rational function looks like? That's a good guess. Y equals. Remember that a rational function is a polynomial expression that's being divided by another polynomial expression. Okay, so they're going to be kind of like the form of 2x plus 3 over x squared minus 1. Okay? Rational functions are just like rational numbers. They have to be in the form of a fraction, and they have to be a polynomial. So again, I can't have like negative exponents. I can't have fractional exponents. I have to have all the same rules for polynomials because I have a polynomial in the top and a polynomial in the bottom. And a lot of times the way we notate that is we say that r of x for a rational function is p of x divided by q of x, where what has to be true? Q of x cannot be equal to 0, because just like any other fraction, I can't have a 0 in the denominator. So when we talk about the domain, what we are talking about is what numbers can we use for x? In other words, what numbers can I plug in here for x? Now, what numbers can I plug in for x? Everything except anything that would give me a 0 in the denominator, right? So remember the way we find our domain is we set the denominator equal to 0. Solve for x. And then the domain will always be all x's except the answers from step 2. On checkpoint 1, they want us to find the domain of these 3 functions. Kind of got offline there just a little bit, didn't I? Yeah, it'll be all right. Where am I messing up? 6. Did I get it in there? Okay. Is it written right? Can you see it? This checkpoint is on page 377 if you want to look in your book, if I'm not writing it clearly enough up here for you. Now, what's step number 1 when I'm finding the domain of these functions? Set what equal to 0? The denominator. So step number 1, I'm going to take what's in the denominator and set it equal to 0. Then what's step number 2? solve for x. So what am I going to do that? Add 5 to both sides. So x is equal to 5. Now, step 3, so here's step 1, here's step 2. Step 3 is what? X minus 3. Check point 1a says x minus 5 on the denominator. Okay. All right. So we used to write this in Algebra 2 that that's all the x's not equal to 5, right? And we use the not equal to symbol. Like I told you in this book, the answer choices in the back are written in interval notation most of the time. And so if I want to say everything except 5, then what I say is from negative infinity up to 5, and I don't include 5, right? And then from 5 to a positive infinity. Good work. Okay, so that's interval notation for that domain. Okay, on part B, step number 1 is to take the bottom, the denominator, set it equal to 0. Now when I solve this, what am I going to do? There's a couple ways we can go about it. It's an x squared, so I can factor, or since there's no x term, I can move the 25 away from the x squared and take the square root of both sides. You want to do that? All right, so I'm going to add 25 to both sides. So I get x squared is equal to 25, so x is equal to square root of 25, which is 5, but remember it is a positive and a negative, right? Because either one works. Right? Remember, when you take the square root, you got to take that positive and negative value possibility. And so now I have two things that my answer cannot be. So on step 3, my domain is from a negative infinity to that negative 5, from negative 5 up to positive 5, and from 5 to a positive infinity. Okay, so you got to drop off both negative 5 and positive 5. You can use it. So that's what that says. It says I can use everything from negative 5 to positive 5. And I'm supposed to have a little union sign in between there, right? Hey, part C. We ready? What are we going to do? The same thing. I got x squared plus 25 is equal to 0. That's step 1. Then I subtract 25 from both sides. That says x squared is equal to negative 25. Now, what two numbers can I multiply together by themselves? What number can I multiply by itself to get a negative 25? Really? 5 times 5 is positive. 5 times negative 5, is that the same number? 5 and negative 5 are not the same number, right? So is there any way I can get a solution where x squared is equal to a negative number? No. There is no way. You cannot take a number, multiply it by itself, and ever get a negative back. Anytime you see this happen, there's no solution here. There's no... Well, we'll talk about that later. Hang on. But right now, what does that mean for my domain? If there's no x that's going to mess me up, then what is my domain? All real numbers. And how do we put all real numbers for the domain? From a negative infinity to a positive infinity is exactly right. Now remember, if I was just talking about the quadratic equation there, that just doesn't cross the x-axis. Remember, it's like above and it opens up. It's got some answers. They're complex numbers, though. But I'm not worried about that when I'm graphing, right? All right, so any questions about that? Mm-hmm. 1:30. Yeah, okay. All right, so the second objective says using the arrow notation. The arrow in mathematics means as it approaches. Okay, so if I had something like x approaches some number, then what I'm talking about is what's going on with my graph as x approaches 2. Okay, now I can be talking about approaching the number 2 from the left or from the right. Okay, so what we do, if we want to talk about it coming up on that number from the left, I put a minus sign. As x approaches A from the left. And if I want to talk about it as it approaches it just from the right-hand side, I put a little plus sign. Okay? Any questions? So, that's not the way we notate it. It has to be a subscript, which is always behind the letter or the number. Now, one place where I do put it in front is if I talk about a negative infinity or a positive infinity. And then I put that on the, like a negative infinity. I put that negative sign in front. I don't use it as a superscript. Okay? All right. So any questions about that notation? We're going to use that to talk about end behavior. When we look at these, there's stuff that happens in the middle that's pretty interesting, but at the end things kind of flatten out, or they kind of do the same thing all the way. And so an application of that is if I had a graph that looked something like this, maybe, like what we had. Never mind one, y'all. Anyway, so if I wanted to talk about this as using arrow notation, then instead of using that rising to the right, the correct mathematical way of saying that is as x approaches a positive infinity. So in other words, as x is going to the right, f of x approaches a positive infinity because it's also going up. So as I go to the right, I'm going up. Over here, I'd say as x approaches a negative infinity because I'm going to the left, f of x approaches a positive infinity. So a lot of times we use this notation to talk about end behavior. That's where it applies. And you just need to know that anytime you see this in mathematics, it just means as x approaches or as y approaches that number. Okay? Any questions about the arrow notation? All right. So, objective 3 is talking about vertical asymptote. Does anybody remember from last year what a vertical asymptote is? What is it? It's like a break in the graph. It's a vertical line that we can't cross over, can't touch it. And where did it come from? Something messed up about the domain. That's exactly right. Vertical asymptotes happen where the denominator of a rational function is 0. Okay, so that's that very first objective when we talked about finding our domain. Our domain is everything except these things that give me vertical asymptotes. Okay, does everybody understand? That's where it comes from. So the process for finding the vertical asymptotes are almost exactly the same. Step 1, we set the denominator equal to 0. And in step 2, solve for x. Set the denominator equal to 0, then solve for x. And then if we were actually to the point where we were graphing this, because that's why we do the vertical asymptote, so we can graph it, then our step number 3 is that we actually draw the vertical line in dashed form on the graph. Okay? So in other words, when I draw in my vertical asymptotes, don't draw a solid line in on your graph, okay? Put a dashed line. But that reminds you that you're going to get real close to that, but you can't cross it and you can't touch it. Okay. So check point 2. We're supposed to be finding the vertical asymptotes, if there are any. We're going to say f of x is equal to x over x squared minus 1. Now, what am I going to do? So step number 1. Set the denominator equal to 0. Then what? Solve for x. So if we add 1 to both sides, get x squared is equal to 1, so x is equal to positive or negative 1. And then if we were actually going to draw that on the graph, then I go to positive, negative 1, and I put my dashed lines in. Okay? That's like step 1 when you start graphing these here in a minute. Any questions about how to do that? Now, let's go ahead and look at part C on that checkpoint. Part B is really not anything different. Except, I don't know, maybe we might better talk about it. Let's do part C first, and then we'll come back to B. Hey, so step 1, denominator equal to 0. And what do we do? Subtract 1. So where are my vertical asymptotes on this one? What numbers, when I multiply it by itself, will give me negative 1? Nothing. So there are no vertical asymptotes on this one. And that does happen occasionally. Now, I don't know if you remember or not from last year, but we do have some things that are holes in the graph as opposed to a break in the graph. You remember those are called removable discontinuities? Does anybody remember how they happened? Why were they removable? Why was it a hole as opposed to being a vertical line where the graph shot off to the north and south? Let me answer that for you. That's when it looks like B. So part B on that one, it says g of x is equal to x minus 1 over x squared minus 1. Now, it's easier if I factor this for you as opposed to just setting the bottom equal to 0. Because if you'll look, that's the difference of 2 squared, right? So it's x plus 1 times x minus 1. So, remember the removable discontinuities were the ones where things canceled out. in the original equation. So I can draw my graph from this equation that's equivalent to it as long as I remember to put my hole here when x is equal to 1. Okay? Do you remember that kind of now? Spent a lot of time learning how to factor that so that we could see the difference between a removable discontinuity and then as opposed to a vertical asymptote. So it's all well and good to set it equal to 0 and then just go ahead and solve it, but all you're finding are the places where you have something that's undefined, and you do have two different classifications of things that are undefined: vertical asymptotes and removable discontinuities, or holes in the graph. Okay? So if you were going to draw this picture, remember what you do. You got x plus 1 is equal to 0. That's a vertical asymptote. So x is equal to -1. But this removable discontinuity, x minus 1 equal to 0, gives you x equal 1. So at -1, I got my dotted line. At +1, I'm going to have a hole in the graph wherever the graph goes. And I'm not sure it's up there. It's just going to be like wherever I draw the graph, I just need to make sure and put a hole in it. Okay? That's the difference. If something will factor out of the top and the bottom, that's what gives you the removable discontinuities. Now, we talked about vertical asymptotes, we talked about these discontinuities, and now we want to talk about horizontal asymptotes. So objective 4. We're talking about a horizontal asymptote. Remember that the way we talk about, the way we discover what kind of horizontal asymptote we have is we have to check and compare the degree of the numerator to the degree of the denominator. Everybody remember this? Okay. And so you get three things that could happen if you've got a top and a bottom and you're comparing them. The degree of the top could be less than the degree of the bottom. If that's the case, then my horizontal asymptote is y equals 0. Case 1. The degree of the top is less than the degree of the bottom, then my horizontal asymptote is just at y equals 0. Second case, if the degree of the top is equal to the degree of the bottom, then my horizontal asymptote is y is equal to the leading coefficient of what's already in the top over the leading coefficient of the bottom. Okay, so I just take the leading coefficient from the top where it is and leave the number there. I'd throw everything else away except just the numbers. And then, of course, my last case is that the degree of the top could actually be the large one. So it could be bigger than the degree of the bottom. And if that's the case, then there is no horizontal asymptote. Now, the difference between this year and last year, because all this stuff is review from last year in Algebra 2, is that we're going to actually go ahead and know that not only is there no horizontal asymptote, but there is a slant asymptote, and we're going to talk about how to find it. Okay, so instead of it being a horizontal line, it's going to be a slanted line. Questions? Y'all got it written down? It is at the bottom of page 381 if you need it. Checkpoint 3. Part A says f of x is equal to 9x squared over 3x squared plus 1. Part B tells me that g of x is equal to 9x over 3x squared plus 1. And part C, h of x is equal to 9x to the third for 3x squared plus 1. Okay, so we want to find the horizontal asymptote. Now, what's the degree of the top? What's the degree of the top here? It's 2. It's squared. What's the degree of the bottom? It's got a degree of 2 also. These two numbers are the same, and so when we said if the top and the bottom degree were equal, then I'm going to take, if the y is equal to the leading coefficient, that being the number that times the x squared term, which is 9, over the number times the x squared term on the bottom, which is 3. So my horizontal asymptote is just y equals 3. Questions about that? Now, on B, the degree of the top is what? 1. If you don't see an exponent, it's 1. The degree of the bottom is 2. Which one's the small one? The top. What happens when the top is less than the bottom? Y equals 0 every single time. Good deal. Now, what's the degree of the top on the last one? And the degree of the bottom? And which one's the big one? So what happens when the degree of the top is the larger one? No horizontal asymptote. It's just that easy. You just got to remember those rules. Yes. Okay, objective 5. We're going to use transformations. Graph these rational functions. And I'm just going to remind you of what we spent a lot of time on last year. So this should be like this. Y'all just going to remember this. My parent function is y is equal to 1 over x, right? Or f of x is equal to 1. That's my rational parent function. Do y'all remember that? All right. So I just need to remind you what it looks like for us to be moving this thing around. So if I want to have any kind of vertical shift, then I'm going to have a over x minus h plus k. Where a does what? What does a give me? Dilation and reflection, right? If a is positive, it's going to go the normal way. If a is negative, it flips it upside down. If a is a number bigger than 1, it makes it skinnier. If it's a number less than 1, between 0 and 1, it makes it wider. Yes? Okay? What does h do for us? It's a shift. It's a horizontal shift, left to right. Right? And k is a vertical shift. It moves it up and down. Okay, so the parent function, remember, looks like this. Starts on the bottom side on this side. It's up in the first quadrant here. There's my parent function, where my vertical axis My vertical asymptote is x equals 0 and y equals 0. X equals 0. And my horizontal asymptote is the y equals 0, right? So that's the part you have to remember, is what does the parent function look like to start with. And then after that, then we can start, doing some different things. So checkpoint 4 says we're going to use the graph of f of x equals 1 over x to graph 1 over x plus 2 minus 1. Okay, so I'm just going to kind of remind you again. Here's my graph. Right? Where the important part of this piece is really my vertical and my horizontal asymptotes, right? Because I'm going to draw within those boundaries. So, according to this graph translation that I've got up here, have I dilated or reflected it any? No. Still a 1 up in the numerator. What have I done, though? Shifted it left 2 and down 1. Good. Now, let me tell you what I actually shifted. I mean, I did shift all the points, but the most important thing to shift is your asymptotes, right? So I've shifted left 2. Which one did I shift? The vertical asymptote, right? So if I was at 0, I'm now going to be at negative 2 because I shifted left 2, right? And then I've moved down 1, so my horizontal asymptote was at y equals 0, so now it's y is equal to negative 1. Okay. And then since I haven't done any other things to this, and this is still the exact same graph, I've just moved it a little. Okay? Very easy to use those translations if they give it to you in that form. Yes. You need to put your asymptotes in with a dashed line. Okay? Because I will be looking for those when I graph them. Unfortunately, they don't always give it to you in this form. A lot of times they give it to you in our rational function form, which is a polynomial on top divided by a polynomial on bottom. So, if that's the case, and that's what they've done, then what we have to do is come up with a way to graph those also. So the last objective here is that we want to be able to graph any kind of rational function, no matter what form it's in. Alright, so our checkpoint 5 says graph f of x is equal to 3x minus 3 over x minus 2. Now there are some steps that you need to go through beyond just plugging this in your calculator and trying to find a bunch of points. Okay, I know that that's what y'all do. I get that. But you also need to have those places because a lot of times on these graphs you can't see all of the points. Because the way your graph, what your calculator does is it plots points and then it drags a line between them. And so a lot of times the asymptotes kind of throw things off because I've got this weird line dragged between 2 points that aren't really connected. So be real careful, and we have to find those things by hand. Then I can use my calculator to get the other points that I need to kind of fill it in. So the first thing we always do is we set the denominator equal to 0. Because that's going to find what for me? My vertical asymptote. And I always look to make sure nothing's going to factor out. Remember, because sometimes it's not a vertical asymptote, it's a removable discontinuity, right? So I'll double check that. Since nothing's going to factor out here, I have x is equal to 2. Okay, I added 2 to both sides. So I'm going to go over here to where x is equal to 2, and I'm going to draw in my vertical asymptote. Because what you're going to do is you're going to build yourself a skeleton so that you can lay everything else in on it. It's your framework. Step number 2 ought to be talking about any horizontal asymptotes. Now, what do I have to check for the horizontal asymptotes? The degree. So the degree of the top is the same as the degree of the bottom. So leading coefficient on the top is 3 divided by the leading coefficient on the bottom, which is 1. So this is the thing that bothers people a lot. When we talk about horizontal asymptotes, that is talking about end behavior. That's not necessarily talking about what's going on right here in the middle. So a lot of times what I'll do on this y is equal to 3, I won't go all the way across. I just kind of come out here and over here to remind myself that out here at the ends, that's what I'm going to get close to. Now there's some other things that we haven't talked about yet. We can find x-intercepts and y-intercepts, right? Do we not have a method for finding x-intercepts and y-intercepts? Plug in zeros, that's right. When I want an x-intercept, I plug in a 0 for y. And when I want a y-intercept, I plug a 0 in for x. Excuse me. So, if I find the x-intercept on any rational function, we're talking about y being equal to 0, so my equation looks like this. 0 is equal to 3x minus 3 over x minus 2. Can somebody tell me something about this that's going to make my life easier to be able to solve this for x? Can the bottom be equal to 0 and give me 0? No, the bottom being equal to 0 gives me something that's undefined, right? So what's the only part that I really need to worry about then? The top. I need to know where is the top equal to 0. So when you find the vertical asymptote, you set the bottom equal to 0. When you find the x-intercepts, you just set the top equal to 0. If I add 3 to both sides, I get 3 is equal to 3x. Dividing by 3 gives me that x is equal to 1. Okay, so I'm going to go over here where x is 1. That is the only place that I can cross the x-axis. When I start drawing in my rational function here in a minute, can't cross the x-axis any other place. Everybody hear what I just said? That's a really big idea. Now if I want the y-intercept, what do I do? Put a 0 in for the x's. So that's a 0. So I have negative 3 over negative 2, which is 3 over 2, which is 1.5, right? So over here on the y-axis, I'm going to go to 1.5, and that is the only place that I can cross the y-axis. Now, you can take this and put it in your calculator and look in the table and give me some other points. Please make sure if there's more than one thing in the top and one thing in the bottom, you put it in parentheses for your calculator to read it correctly. But because we know that I've got to cross through here, right? And I know it's a nice smooth graph, then I know that this is going to come up here and get really, really close to that horizontal asymptote. And it's going to come down here and get really, really close to this vertical asymptote. Right? So I pretty much got that side figured out. Now, can I start down here on this one? Because I've got to come to this one, and can I cross this x-axis right here? So where does that force the other piece of this to live? Up in that top quadrant up there. Okay, so everybody see how I can kind of estimate where the graph's going to go based on the things that I know just from these 4 pieces right here. Again, just to make sure, though, you can always use your calculator to find out some more points and plot some more points and get a nice smooth curve. Okay? And I always advise you to, step number 4, plot some extra points. I wouldn't think about getting all my points from the calculator. because again, you're going to miss some of them just because of the way the thing's drawn on the calculator. But it is pretty safe to get some extra ones after you found these. Okay? Any questions on how to graph this? Mm-hmm. Mm-hmm. Well, I knew that I couldn't. This asymptote means that I got to either start down here or up here. And if I had started down here and knew that I had to get to that, right, because that's my end behavior down there, then the only way that happens is if I've crossed the x-axis here somewhere, and I can't cross that x-axis. Because that's why I said when I find this x-intercept, this is the only place. I cannot cross the x-axis anywhere else. That's why it's such a huge idea. Okay? But again, you could have got those points out of your calculator. Just look in your table. Okay? Anybody else? All right. So, like I told you, we have some that have a slant asymptote, and that's the piece that's being added. Nothing else that we've done here is new. I don't know if you remember it or not, but we did all of this in Algebra 2. The new piece of this that puts this up college algebra is that now we have some slant asymptotes. So, let's try checkpoint A. So we got f of x is equal to 2x squared minus 5x plus 7 over x minus 2. Now, how do I know this has a slant asymptote? How was I able to skip right over and find the one that's got it? The degree of the top is bigger than the degree of the bottom. That's how I know. Every time that happens, there's a slant asymptote instead of a horizontal asymptote. Now, this is how you do slant asymptotes. You actually divide. Okay? When you divide by the slant asymptote, then that gives you the equation for the slant asymptote. Okay? So, if you're following me, I have jumped over to page 387. Okay. And they were nice on this one that they gave us. We can actually do synthetic division with this, right? Is it in the right form for synthetic division? Yes, it's being divided by x minus a number. So I'm just going to pull this out. There's my 2. 2x squared minus 5x plus 7. And then bring down the 2. 2 times 2 is 4. Add that gives me negative 1. Get negative 2, and I add that and I get 5. Now this time, what we've always used in the past is this remainder, right? Well, I don't use the remainder. The equation of the slant asymptote is always that piece that we get. It's the quotient here, but without the remainder. So the equation of this slant asymptote is 2x minus 1. Remember, I put the x on there, and I reduced the power by 1. So it started out x squared. It's now x to the first. Okay? Is that easy? Okay? So in other words, when I start graphing this, then when I do my end behavior, my equation 2x minus 1 dot would give me an asymptote that looked like that. Okay? That's what it means. So that's the only piece that's added to it are those slant asymptotes. And a lot of times on the test, they don't actually ask you to do a graph with the slant asymptote so much as they just want you to be able to find it and come up with the equation of the slant asymptote. So most of the time at this point you'd be finished and you'd never be graphing one of those. Anybody got any questions about that? And then of course, just like every other section, in this section we have the application problems. And I do need to say something about the application problems this time. I'll wait. Well, let's put it this way. You're going to have a slant asymptote as long as the degree of the top is just one bigger than the degree of the bottom. Just one bigger. Don't know. Never had that happen. Hadn't really thought about it. All right. So anyway, on applications, the reason I wanted to say something to you is because I want to talk to you about average cost. This is a term that's used in business a lot. We see it all the time, you just don't think about it that way. Every time that somebody orders T-shirts, I don't know if you've ever been part of actually ordering the T-shirts other than just buying it because somebody had it to pay for. But when you order T-shirts, they'll tell you, or a lot of things that they'll tell you, if you get less than 10, the price is one thing. If you get from 10 to 25, the price is something else, and over 25, you get a different price. And the prices go down, right? That's because on a lot of items that when you make it, like especially like T-shirts, you got the fixed cost of just the basic T-shirt, right? But there's also a cost of setting up the screening, the silk screening process, where you set up the machine to do the silk screening. And so that's pretty time consuming actually. And you have to pay somebody for the hours that they spend actually setting the thing up. So that's another cost. Well, you just set it up once for the whole run. So it's not like every time you do 10 shirts, you got that cost again. You just have that cost one time up front. And so the way you find the average cost is you take just the overall cost or the total cost of doing a project, but then you divide it by the number of items. And that'll tell you how much it's costing you per item. You understand what I'm saying? So in your book, and you're going to see this again if you go to business calculus or regular calculus, they talk about average cost a lot because it's a big idea in business. You take the total cost and you divide it by the number of items that you're going to be selling. Normally, the number of items that we're going to be selling is notated as an X. So average cost is normally the cost function divided by X. Everybody hear what I just said? They're going to give you a cost function in your problem, and for you to get average cost, you need to put it over X, which is why it puts it in this section, because now it's what kind of a function? It's a fraction, which makes it rational, right? Good. So, just reminding you about that. Any questions at all? Okay, so let's go ahead and give you your homework. It's on page 390. Five through 80, multiples of 5, and then I want you to do problem 90 and 92. It's a word problem.